accueille Youssef Moulane, qui est un brillant astrophysicien, qui n'est pas seulement un astrophysicien, qui est aussi quelqu'un qui essaye de penser justement ce qu'il fait, c'est-à-dire de penser le regard qu'on a sur le cosmos. Et c'est de ça dont il va nous parler. Évidemment, c'est un regard qui change. Et comme vous le savez, notre thème, je ne vais pas le répéter des milliers de fois, c'est le thème des transitions. Et donc là, on est dans le séminaire qui est certes à l'intérieur de l'IAS, mais qui est en particulier le séminaire de la chaire des transitions, dans laquelle dont je suis plus ou moins le lead, et où on a d'autres représentants, plutôt plus que moi. À toi la parole.
Merci Raphaël pour cette belle présentation. Ici, merci pour l'équipe pour m'inviter pour ce séminaire. Et quand on parle de chef, je vais shifter vers l'anglais, comme ça je trouve moi-même confortable de donner exposer mes présentations. So thanks again to the team for inviting me. And actually, I'm enjoying a lot your book that you wrote, two of you, so as a chair of the transition, Marwan and Raphael, about the transition. So and I'm enjoying it. And actually, I'm seeing a lot of things. So I'm learning a lot of things from that what we have wrote, and also all the experts that they participated in one of the science weeks here at UM6P to talk more about the different shifts and different transitions happening on different fields. So that's really amazing. So today we will be talking about something specific, not I think, well, I'm not sure if it was covered, maybe I did not arrive at the book at the end, but we will be talking about one of the main paradigm shifts in our understanding of the cosmos. So it does not mean that I will tell you all about the shifts that's happening. So this is going to be take half day or 1 day just to explain. So I will try to summarize the main ones that's happening in the cosmos, in our understanding of astronomy and space science in general sense. It's when people start thinking about it. So for like 100 or more than 100 years ago. And I will not focus only 100 years ago, but some also the recent shift that's happened only in the last 20, 30 years with the advanced technology that we are having today. So the main paradigm shifts that I'm highlighting here. So the first one is about, and I think Enes and Bruno talked already about that. So from the Newtonian gravity to the general relativity and what Einstein bring to us and how it changed our understanding of the gravity and how it works with the space-time curvature and all of that. I will talk a little bit about it. Then we will talk about what we have learned from the expanding of the universe after the Big Bang, since the first discovery by Hubble, who discovered that the universe expanding by measuring how the galaxies they are getting away from each other, and what's the recent advances and tools that we have today to learn more about that. And most importantly, and I'm going to focus on that because that's the topic of the I consider it one of the main shifts happening in our understanding of the cosmos, also in astronomy, which was the rise of astrobiology and exoplanets, and that will bring the question of if there is a life beyond Earth. And this is one of the things that inspired me and also shocked me about which kind of transition or shift that we are having in this field of exoplanetology or in planetology in general. And lastly, I will talk about the role of the technology, and this is also I consider it one of the main, because the main shift that it's happening in astronomy, because when we talk about astronomy, of course we do theory, so we do calculation, we do models, we do all things, but without observation we cannot confirm things. That's when we talk about observation, we talk about telescopes, we talk about technology. That's as human we are developing to try to answer one of the main questions that fundamental question that we still did not answer yet, or we're still progressing in understanding this question about the origin of the universe, how the universe works, where the universe come from, and where we are actually, which is, I consider it like we are stupid, we still not reply to this question, where we are. So where some of you say, okay, we're on the Earth, which is just one of many planets around the star, and the star is just one star of billions of stars in a galaxy, and the galaxy is just one galaxy among billions of galaxies in the universe. And we still did not find the ending, so this means that we still not answer that question. And we are progressing on that, and we are finding one of the main shifts in our understanding of the universe in general by this recent and observational data that we are having. So before starting, I would like to highlight this citation from two guys, which is the first one, which is Edwin Hubble, who I consider one of them the key player in this our understanding of the universe, because he's the first one who doubts about the expanding of the universe. So he said that the history of astronomy is the history of receding horizons. It means that there is still a lot of things to discover, and we're still doing that. And until today, we still did not know a lot of things, and we should looking for that horizon and trying to improve our knowledge, trying to acquire knowledge to understand these questions. And the second citation is from Carl Sagan, which is, I will not read it all of it, but only the last one, the last sentence of his citation, which is say, somewhere something incredible is waiting to be known. And this is still applied every time. So wherever we go, so we still have a lot of things we still did not discover. And this is why every week, every month, every year, we have a new discovery happening in the field of astronomy and astrophysics in general, which is help us to progress our understanding of the universe that we are part of it. So taking that, so trying to define, because when Marwan asked me about giving this presentation and talking about the shift or the transition happening in astronomy, and I did not understand the question. So I said, well, so there's a lot of, I consider it not a shift, but it just kind of continues progress or accumulation of the knowledge that we are getting to understand things more. We're not shifting from one phase to another phase. It just, and trying to redefine this shift as not a new data that we are having, but it's a complete change in the framework we use to understand the data and also to interpret the data. So, and of course, in astronomy and astrophysics, we have it's experienced a lot of revolution, which is I'm going to highlight today in this presentation. And I will start with the first or one of the main changes or shift that we have in our history, which is happening like 400, 500 years ago, which is thinking about our solar system or our universe in general, from geocentrism to the heliocentrism. And there's a lot of people pay that off just to prove that the heliocentrism is the right thing. And the geocentrism was considering, for who now, I believe that you're familiar with that the Earth is the center of everything. And this is very simply clear, because when you look at the sky every night, you see things moving, and we consider ourselves for fixed, and everything is moving. And this is what was the model was popular at that time. So thinking everything, galaxy, everything is moving around the Earth, and the Earth is the center of everything, and we are unique in the universe, and so on. And this was supported, of course, by the beliefs from religion and so on, and until like almost 1,400 years. And until the Copernic came and trying to explain that, no, we are not the Earth, we are not in the center of the universe, but we are just one planet among others orbiting around a star, which is our star. And all the stars that we see in the universe, it's just like other suns like our sun that they might also evolve in. And this was proposed by Copernic and as a circular orbit. And then Galileo's use, and here we're talking about, when we talk about the shift of technology, we're talking about Galileo, who was the first one used his telescope to prove that. And he was observing mainly the Jupiter moons and also the Venus phases to explain how we are just planets rotating around the sun. And of course, when Kepler came with his equations, and he fixed that with this not our circular orbit, but they are elliptical orbit, and he established some questions and laws, one of the 3 laws of the orbit of explaining the orbit of the planets and all the objects in our solar system. And after that, Newton came also with explain how that works with the gravity. But until here, it's still not really like a complete explanation of how gravity or how our solar system works in general. So by the end of the 1600s, so the heliocentric model was really accepted by the community. I mentioned some people paid off, like Galileo, because he was I think attacked by the religion people that this is not right. So, and they even, I think, kill him and so on. So, and this is not only him, and many other scientists who was believing on this heliocentric model and so on. So from this, we understand that this was the first I consider the first major revolution. So maybe some people will not consider that, but I consider this is one of the first shifts that's happened in understanding of astronomy. So from shifting from having the Earth as the center of the universe of everything to another planet, just another planet orbiting around the sun, which is there are many billions of other stars in this universe. And the second shift is about trying, well, when Newton introduced the gravity and the way how he explained it, that was enough growth in his Principia book. Everybody was like celebrating and also congratulating Newton for doing that. So this was in 1687. So like gravity is a universal force and it works the same everywhere and so on. And this is actually was not was another revolution. I will consider that is the gravity is and he explained that with his equation, which is the force between two things. And I think you have also heard, all of you heard about the history of the apple when he say why this apple fall down and why did not go up. And this is how he explained the gravity and he established his equation. And this was another shift from understanding the Newton mechanics to the gravity as a universal force that can explain everything, even between planets and also between the moon and the Earth and so on. And this is, I will consider it also another shift that Newton used to unify the terrestrial and the celestial mechanics, showing that the same laws govern both. So even some things happening here, how this gravity works on Earth is also work on the solar system in general, like between planets and between the moons and the planets. Now, we are moving to another shift, and this is, I would consider it also, and by the way, this is the shift that I see from my point of view. So there are many other people like thinking differently and considering different shifts, and they will not maybe consider that is a shift and so on. But my way how to say things, because when I was thinking about it, I tried to organize it on this way. So the next or the second shift that's happening in understanding of astronomy and astrophysics. So when Einstein came with his famous theory, which is the general relativity, on special and general relativity, and he was explaining that and confirming that the gravity does not work how Newton described it, but it's not a force between two things, but it's just a curvature of space-time, and he established that with this famous equation of the general relativity. But that he makes some trouble for us having this constant here, because when he found the term he did not explain it well, so he make it as a constant, and we are still struggling to know what this constant is here, which is we called it the cosmological constant, which actually represent the dark energy or the energy that's responsible for the expansion of the universe, which is representing like more than 70%, and of what we know about the universe, and that's replaced the Newtonian gravity with the space-time curvature as explained, establishing the general and the special and the general relativity. And this was also confirmed by bending the light. So when the light is coming from a far away place, like from another star, and if there is an object, it could be a star or a galaxy, the light will not come just straight away, it will curve, and this is what we call the lensing. And also this was proved by the gravitational time dilatation. So when we have, and this is actually we're using that in our daily activity with the GPS satellite and so on. So it's actually the GPS satellites are using the general relativity to have precise measurements of time. And also they predict that black holes and also gravitational waves, which we just have discovered in 2015. And imagine, so general relativity was established in 1912, and yeah, between 1905 and 1912, and it was predict that we will have gravitational waves. Gravitational waves are waves that produced by a merger of two massive objects. They could be neutron stars or black holes, as you can see here. And we did not discover this signal like we have been trying like for many, many years until 2015. And the first time we discovered with the LIGO and Virgo experiment based in the US, we discovered the gravitational waves, and that confirmed one of the big revolution also happened in astronomy and astrophysics, which confirming that we can detect. Imagine that we have an object that farther away from us, and we can feel that they merge. by this gravitational waves that we have confirmed, and thanks to the Einstein for explaining how the universe worked by his new theory, which is the general relativity. So for this shift, I consider that Einstein redefined the space-time in his equation, even if it's not 100% complete, because we still have a lot of things, we still did not understand a lot of things, and that is coming from his cosmological constants. So, but he explained that the gravity is not a fixed background, but it's a dynamic and inactive with the mass and energy, and this is what he explained in his theory, and was confirmed later by the detection of the black holes, the existence of the black holes, who also proposed that, and also the detection of the gravitational waves. So now we'll come to another shift that also I consider it with just a big moment when we discovered that the universe is expanding. And thanks to the Edwin Hubble, who used his telescope, and he was measuring the distance of the galaxies with the speed, and he found that there is a good correlation, and this is one of his plots from his paper, showing that there is a nice correlation between, at that time, he did not use a lot of data. Even you see this, there's no error bars, and the data are spread out. But we can clearly see there is something happening here, which is there is a nice slope between the distance and also the speed of galaxies. And of course, in 1965, and John, he just came in the right time when I'm talking about CMB, one of the big, one of the cosmologists in France also working on the CMB. So, and he just finished one of his seminars that he was giving to at our institute there. So I'm talking under his supervision. So if I do something wrong, he will correct me. So when I have the CMB, I will talk more a bit about what is the CMB exactly. And you see here the experiment that we have running to detect the CMB. So you see how it changed from experiment to another with the time that we are. This is one of the major shift in technology that I will show later, that we are, as human, we're advancing to understand the cosmos in general. So, and also we understand that the universe is not static, it's a dynamic universe, and this is but we still have more open questions. So when I'm talking about shift, does not mean that we understand everything, but there's still a lot of things to work on, which is one, what is about the Big Bang, how it started. So we did not understand fully the quantum gravity that maybe can play a role in the Big Bang, or there are some ideas about there's not only one universe, maybe there are multi-universe. There is still a lot of things we did not understand. And also we did not understand or know what is the composition of this universe that we are describing, which is dark matter and dark energy. So dark matter, which is representing like more than 25% of the universe, which is invisible mass holding galaxies together. So when we say dark, does not mean they are dark, because just we don't see them and we don't know what they are. So we just give them this name, dark energy or dark matter. Dark energy is almost 70%, which is one of the mystery of the force accelerating the expansion of the universe. We still did not understand. There are some theories that trying to explain that, especially the inflation theory. So John can develop later more about it. So that we are trying to explain what we are observing in the CMB, the cosmic microwave background. So the idea of the beginning of a universe that's evolved over time was a radical shift from earlier beliefs in a static cosmos that we are studying today. So here I'm making this map in really large to see, and to tell you what you are seeing here is just when the universe was baby, was like almost 400,000 years old. So what we are looking here is the fluctuation of the temperature of the universe when it was at that time. So that's if we believe that in the Big Bang it happens. So what we see here is the fluctuation of the temperature, which caused by this inflation that I talked about. And also this may be caused by this gravitational waves that we call it the primordial gravitational waves, was responsible for creation this kind of structure that you see here. The blue spots are the cold places, and the hot spots are the red spots are the hot places in the universe. When this is our first photons that we are seeing after the Big Bang, when the matter and the radiation decouple at that time. And this was taken by one of the advanced experiments that we had so far, which is Planck. And now there are more other missions or other experiments that we are running to understand and find more about this CMB, to understand the origin of the universe, which is one of the main fundamental questions we still did not fully answer. So here I'm showing in general, I'm not a cosmologist, but I'm just trying to see what we are trying to understand about the universe and what is the, this is one of the timeline of the Big Bang theory that when it's happened, so we got the inflation and the CMB just right here. And then we still have what we call the dark age. So we don't understand yet how the first atoms, or the first stars and the first planets and the first galaxy formed. We know how the first atoms was formed, the helium, hydrogen and helium and lithium through the BBN nucleosynthesis, the Big Bang. And we have also, now we're looking in this place. So we did not have enough or more powerful technology to look at the edge of the universe. We are advancing, looking for farther galaxies, but we still did not, we still have more open questions about different areas here, how they evolve and so on. So back to one of the other main shifts, so as I mentioned, which is I'm going to develop in it more, which is almost my specialty, when we see a lot of shifts and it's happening, which is the rise of astrobiology. So when we're talking about astrobiology, we're talking about life beyond Earth, so not on Earth. And this is one of the main hot topic that we have today, which is life beyond Earth. And we are trying to look in the ingredient of life somewhere else, not on Earth, and to see if our Earth or our planet is unique among other trillions of planets that we know today exist in this galaxy and in this universe. So just to know, to explain that astrobiology, it's a mix of two things. So astronomy, of course, and biology, which is looking for biology somewhere else. And this is also a new kind of astronomy branch. It became into birth, and we are working on that, especially on the exoplanets, finding other planets around other stars. So there is astrobiology and biosignatures. They are two different things. So, and this is also one of the, maybe you consider it one of the science fiction fields, which is the biosignatures. So today, as humans, we are looking for signals coming from other civilization. And this is, I will consider it also one of the main topic in the today that we call it SciTE, which is a search for intelligence signals from somewhere else. And there are some countries or some people working on that, trying to point their telescopes to find if there are some signals coming from somewhere else, and we are not alone here in this universe. So these two things, astrobiology and biosignatory, actually it's having the multi-field, so it's combined biology, chemistry, astronomy, planetary science, geology, everything to understand this question about is there is life unique on Earth, or this is life is maybe common, or there is maybe other forms of life that we have no idea about. And to understand that, we have to understand the life on Earth first, how it works, and if we want to look for something somewhere else, we should know what we have here on Earth. So I always list this 5 criteria, so maybe they might plus or minus, so to have them to have life. So first we need what we call the right chemical elements to find life as we know. So we know oxygen, we need it. So we need carbon, hydrogen, silicon, calcium, all of these things and many other chemical elements. We cannot live today without them. And also they are present in our plants and animals and everything. So we need really liquid water. And this is really proportionally related to the life. You know that in the South Pole or the North Pole, well, it's very hard to live without having liquid water. So there is no plant. It's very hard to have a life as we know. So we need the very range of the temperature, not cold temperature and not hot temperature. So it should be some equilibrium. So to have established kind of life and so on. And also we need an atmosphere to protect us from all this radiation that's coming from the universe. And thanks to our atmosphere and also the magnetic field that we have in our planet that is protecting us from many radiation that may kill us and also destruct the life on Earth. And we should also have enough gravity, means that the planet should be a bit big comparable to the Earth. If it's small, you cannot really plant things or make things because the gravity will not be absorbing, taking things. So we should have something is maybe closer to the Earth or much bigger a bit to the Earth. And if we have this condition, we consider ourselves we are in the habitable zone. And this habitable zone has many, many definitions, but there are some people considering many things. So, but well, so if we want to talk about a common definition, is we have in this criteria, and then we consider this planet as a habitable zone. So simply, it's an habitable zone. It's a zone where it's not cold and not hot. It's just between. Not hot to be burned by the sun or to be affected by the radiation of the sun, and not cold to not have the water on ice form, which is, we should have it just in the right, in the zone which is green here, which is like, and that's depend on the star. So I will show you some examples. So if star is big, this habitable zone should be further away from its star. If it's close, if it's small, this habitable zone is moving toward the stars because the radiation from star will not be enough to have water as a liquid in a liquid form. And we explain that with this graph. So it depends on the stars. So for example, this is our sun. So we have here this habitable zone is defined by this phase here. So you see here there is some planet that you know, Earth, and also Mars is just on the edge. But we can consider it on the habitable zone. And we have other planets that we have found around other stars that's smaller than our sun, and they exist also in the habitable zone. And this is just to show to you that this habitable zone, it's moving with respect to how the star is big or small compared to the sun. There are other stars much bigger than the sun, so the habitable zone will be much farther away from its star. So before looking for life beyond Earth outside of our solar system, let's look for it inside of our solar system. And that means let's start with some places that maybe we doubt that there is some life there in our solar system. I will highlight some, maybe not all of them. Mars, of course, and Enceladus, and Titan, one of the main, one of the moons that we believe that they might host some kind of life. So let's start with Mars, our neighbor, because it's easy, not easy, but it's easy to go there compared to other planets. So in Mars, we believe that there was water there for a long time ago, and somehow Mars lost his water for a reason or another. We don't understand yet what's the reason that was responsible for, because it has also an atmosphere, and it lost its atmosphere, and directly it lost also its water. And this is also maybe going to be the future of our planet if we do not take care of it. This is one of the two reasons why we are studying Mars, to understand if it's, and this is why NASA and other space agencies, the ESA, they are spending a lot of money to try to test and find if there is any biology life on Mars. It has evidence of life was on Mars, and we are trying to do that. And this is just to understand if this was only a unique for Earth, or just as because its neighbor also was hosting life, and maybe if we do not take care much about our planet, it's going to be like Mars, like that, losing its atmosphere and losing. And why Mars? Because Mars is closer to us, so we can send robots and we can do easily observations, and to try to test all of this thing and try to understand this question of having life beyond Earth. And then we have Titan. Titan, one of the is the largest moon of Saturn, one of the planets Saturn, and is the only moon only object in solar system has an atmosphere like our Earth. And this is one of the criteria or the condition I have listed. So Titan has an atmosphere, and it also have it's a terrestrial. It has a ground. And it's full of methane, but not only methanes like in the atmosphere, also lakes of methanes. And also, maybe if we have our life, it's based on the water as a liquid, we might have another form of life based on the methane. So who knows in this kind of condition of Titan. So that's why we're interested to, and this is one of the real picture of Titan, as you see one of the ground-based telescopes to see its atmosphere. But now with James Webb, we are learning more about the atmosphere of Titan, and this is one of the pictures that was taken from the ground of Titan, where the mission was sent to this moon by NASA. And you see here's a plot, a graph showing all this organics that exist on the atmosphere of Titan. We are even progressing on that by sending a space mission. NASA sending this Dragonfly. I'm not sure now it's going to be happen or not with Trump. So they are trying to make some reduction on the budget. But the idea here is to try to send a helicopter, which is Dragonfly mission, to the surface of Titan and try to visit different places. And this is why helicopter. So it's a kind of not helicopter as we know. It's kind of a small laboratory. It's full of instruments, try to measure in all the components of the surface of Titan, and also when it's going through the atmosphere to learn more about this moon and if it's having any kind of life. And this is planned to 2026, 28. We're not sure if it's still going to be happen or not, but this is one of the ambitious or the future mission that NASA is planning to send this mission about this question about finding life beyond the Earth. And also, I will not miss talking about Enceladus. It's one of the moons of Jupiter too, but this is weird, a moon. Why? Because it's full of ice, which is crust of ice. But we have seen, not recently, a long time ago, we have confirmed that recently with James Webb Telescope, some plumes from the south pole of this moon. And these plumes, they are basically coming from the sub-ocean that exists under this crust of Enceladus. And we believe that this is also full of organics actually. We did that with James Webb and with other telescopes. And we believe that's because of what we call the hydrothermal vent happening in the bottom of the ocean of Enceladus. And this also exists in our oceans, and we have seen them. And this is one of the real videos that you can see. So the analogy here is, okay, if there is this hydrothermal vent on Earth, this should be also exist and responsible for the plumes that are crossing the crust of the Enceladus and making this plume that's having some organic when they come through the ocean. So why I'm showing this hydrothermal vent? Because this hydrothermal vent on Earth, it has also some kind of life around them. There's extremely hard environment, but they have a lot of animals and a lot of bacteria living around this environment. So, and you can see some of them here. So this is in the bottom of the ocean. So why this could be a life on Earth, and why not maybe on Enceladus? And that's one of the main questions that we are trying to understand. Of course, it's going to be hard to go to the bottom of the ocean of Enceladus because the crust is almost 100 kilometers. Which kind of technology that you can have to dip and to dig in this 100 kilometers to go inside of this bottom? But who knows? Maybe one day we have a genius who can discover something that we can create a big hole in this crust and go to the ocean of the bottom of the ocean to see if there is kind of life or not. So here we looked about life around surroundings, so in our solar system, in Mars, in other moons closer to us, but we will not just stop here. So this is a view of our galaxy. Actually, this is not a real picture because we have never been outside of the galaxy to take this picture. It's just kind of illustration, and we can make it from what we are seeing in the galaxy, and we are somewhere here. So this means there is not only our planets, there are many other planets around other stars. And that's the question. So how many stars are in the galaxies? So almost up to 400 billion stars in our galaxy. So the question here is there is no planet around this billions of stars in our galaxy? So people have asked this question a long time ago, but it was very hard to detect them because we didn't know how to detect this kind of planet, which we call exoplanet, until those guys came, Didier Queloz and Michel Mayor, who they won the Nobel Prize in physics in 2019, who the first one discovered an exoplanet outside, a planet outside of our solar system, which is about, it was in 1995 around the star called 51P Gassi b. So when we discovered that, so today, and they discovered that through one of the methods we called it the radial velocity, so looking how the star is moving around its planets with spectroscopy. But today we discovered more than 5,000 exoplanets with this transit and also other methods around other stars. That means that our planet is not a rare or unique thing in the universe. There's many other planets at least in our galaxy that we discovered, and we believe that there are also in other galaxies that we have billions of them. So And that's the statistics that we have so far since 1995. And this is one of the methods that we use for discovering this exoplanet. Today, in 25, we are almost on 5,800 exoplanets confirmed, and there are trillions of exoplanets exist still waiting to be confirmed using one of the advanced methods that we are trying to apply. So we were talking about, this is our variety of planets. So us in our solar system, not all the planet looks like our planet. So we have, for example, Jupiter and Saturn. They are gas planets, so it's very hard to have life there because they are gas. And also we have Uranus and Neptune. They are icy planets. It's also hard to have planet there because they are farther away from the star, means that they are not in the habitable zone. So we have only 4% from all this 5,000 planet that we have find so far. We have only 4% are terrestrial planets, looks like our planet, which is we can look for life in, because that's only the kind of planet that we are thinking that they might have some life around them. And we have many others like hot Jupiters and like super Earth, and this is mostly going to be gas or ice planets, which is they might have not support any kind of life as we know. So one of the ways or the methods that we use is the transit methods. This is one of the, it's just a simple idea, but how to apply this idea and how to make it happen, it's a really shifting. So the way is just to look at the star and try to see its brightness. If its brightness is damping, it's diminuting, so it means that there is something passed between us. It should be in front of us, between us and the star, and that thing, it could be only a planet. And if the thing is dim of the light is small, it's going to be small. If the planet is big, like Jupiter or something bigger, so it will be, the diminution of the light will be much deeper. And this is how actually one of the common methods that we use to find exoplanet, and we are still looking for more planets. So in this one, I'm sharing one of the, what we call the potential habitability exoplanets, means that the fit or the field, the criteria that I have established, so they are not far, they are not closer to their planets. We have a list of them here. And by the way, here you have how they are far away from us. Means that even we find a planet that maybe hosts kind of life, we will be never going there. Why? Because they are farther away. The closest one to us is 4.2 light years away from us. Means that we have to travel with the speed of the light for 4 years to get to the first planet. And this is impossible with the technology that we have today. So the speed of the light is 300,000 kilometers per second. We are not reaching only 1% from the speed in our technology that we are producing today, and so on. So that means that, well, there is no, and this is one of the citation of Michel Mayor, who discovered the first exoplanet. He said, there is no plan B, so we should take care about our planet. Now we're just wondering what is there, but we will never be able, at least with the technology that we have today, to go to this planet because they are far, far away. So, and this is the only one. The second closest one, it's 11 light years away from us, and so on, and so on. So it means that we are challenging our technology, how we can find life in this exoplanet, even they are far, far away. And in this planet, I'm highlighting, as you can see here, some planet, they have a common name, which is TRAPPIST. And I will tell you the reason why I'm highlighting this TRAPPIST-1D, TRAPPIST-1E, and TRAPPIST-1F and G, because in 2017, that was the first time we discovered 7 planets at once. We used to discover 1, 2, 3 exoplanets, or the planet around the star, but this time we found 7 at once around the star, which is like 41 light years away from us. And this is used by two twin telescopes, one in Chile and one in Morocco, in Camden Observatory, and this is why I'm highlighting, because there are many. So, and actually I used to use these 2 guys during my PhD studies to not look for exoplanets, but to study comets, because also with comets we have learned a lot how they maybe contributed to the life which is we are looking for in our planet. Maybe also can explain it how it works on other planets. And yeah, and I had the chance to work with these telescopes, and especially with Chile, when I spent a couple of months there in La Silla in Chile, and also I had the chance to visit other telescopes in Pará and in Alma. And that's what it motivated me to continue and to work on during my PhD, and after that in astronomy and astrophysics, and learn more and more about it. So this is the TRAPPIST system. There are 7 planets. and they are similar almost in size, and they are closer to their stars, and that's because their stars it's smaller than our star, and I will show you a comparison of that. But the important thing here that there is not only 7 planets, we discovered 7 planets at once, but 3 of them, D, E, and F, they are exist in what we call the habitable zone that we have just talked about. And this has never been found before. And this is why we're excited about this planet. Now James Webb Telescope is looking at this planet to find any signs of the life on this planet. And if we will compare to the system in our solar system, they are, by the way, so they are short orbital planets, a couple of days. So I will always use the joke, if you live on the system, so you'll be maybe older than now, because they complete 1 year only in a couple of days. This is what we see here compared, for example, to our planet, which is need almost 365, 66 days to complete 1 year because their star is small. So yeah, so you see here they are almost, especially these 3 are comparable to the Earth in terms of the density and in terms of the mass. And this is what is important also to see if there is enough gravity there to have. And also they exist in the habitable zone means that they support the water in a liquid form. So if we want to compare that, so we can take whole TRAPPIST system and we can just bring it in the orbit of Mercury. Why? Because the star here, we call it M dwarf, because it's much smaller than our sun. And that means that the whole system will be closer to the star because it's small, not like the case for our sun, because much bigger than this one, so the planet they're gonna be. And this is one good example to show how this habitable zone, it's moving based on the size of the star. So, well, good, we found these planets, we are finding more. So what about the life of this planet? I showed to you the way how we found them is just to look into the diminution of the light. So now how we can go and explore if they have atmosphere, if they have liquid water, how we can really confirm this kind of detection. And for something that we don't see them actually directly. And this is what we are doing with them. So we don't see in the planet themselves directly, we're seeing just indirectly with the diminution of the light of the stars. So now how we can probe or how we can find or confirm that they have some kind of life. And that's very challenging. And this is why I consider one of my last axes about the technology that we are improving today to understand more about this exoplanet. So, well, the idea again here is simple, but in reality it's hard, is we are looking the light when it's traveling through the atmosphere of this planet. So it depends on the atmosphere of this exoplanet, of this planet. It will excite, or the molecules are there, they will excite or emit light. And from that we can use spectroscopy as a technique to understand or to know which kind of molecules that exist or atoms exist on the atmosphere or in a given exoplanet. But for this one, we need a really high resolution and also bigger telescopes to do that. We cannot do it with the small ones. And this one of the techniques that we use is, again, the spectroscopy, but this time we do it with the transmission. So first one is just the photometry when we detect them. So we just look at the light, how it's changed with the time. But now we can put a spectroscopy when the planet is crossing. And we see how this depth is changing at different wavelengths. And from that we can interpret how the exoplanet, what is the exoplanet, or what is the atmosphere of this exoplanet? It has a thick atmosphere or a thin atmosphere, or which kind of molecule that could this planet support. And this is actually, it has been done, and I will show you some results that we have obtained with the James Webb Telescope. But we still have more open questions because this will never end. So the new questions are, well, again, the Earth is still unique. But what we are seeing now is likely not, so not unique. So we have many other planets looks like our planets, and now we are finding them. So again, what's count as a life? What is kind of life? Is the life as we understand it, or maybe there is another kind of life that we have no idea about, something that we should be some life based on carbon or maybe water dependent. And also where we'll be finding intelligence. And now we are trying to look for the signals in this alien stack or somewhere else. it might exist, it might not, but we never look at it. Now we're trying to look at it, and this is one of the, I will consider that's going from just wondering about aliens of life and seeing them on our science fiction movies. Now we're trying to test that and try to use our technology to detect if there is really something or we're just dreaming about that. So, and I will finish with this axis about, in all of that, the technology really played a big role on advancing and shifting on our understanding of the astronomy, and I will highlight some examples. And if I want to summarize that in one picture, this is the Galileo telescope that Galileo used the first time to look at Jupiter, and this is what we have today, a telescope which costing $10 billion, which is looking for life beyond Earth, looking for life like thousands and hundred light years away from us. So this is, if you want to summarize everything about what is the advanced, this is one of the first telescopes was used to observe, and this is one of the last advanced telescopes that we are as a human, and we still progressing more and more in the technology. And this is only, I mean, James Webb is one of the most optical or inferred powerful telescope, but we have other telescopes advancing, like looking for CMB, like when the universe was young, and this is another advance that there are more experiments and telescopes are coming to teach us more about the our way of understanding the astronomy. So I will also highlight another telescope which is under construction now. This is one of the telescopes is in Chile, extremely large telescope, which is European. We're talking about a telescope with we started with this small unit of Galileo. Now we are building a telescope with a 30-meter in diameter, and using different technology like optic adaptatives, like we're correcting the atmosphere that disturbing our light, and we are doing novel technology, try to characterize more this planet and try to understand more about if there is this life there or if they have atmosphere and what is their composition and so on. And this is one of the spectrum that we are getting as a first science result from James Webb Telescope. Now, this is one of the first spectrum showing that the first molecules that we are finding somewhere else. We're looking about water is here, dioxide carbon, sulfur, carbon monoxide, sodium. All those things they exist on other planets, which is like it's farther away from us. And we are taking more data to learn more about this exoplanet. Just 30 years ago, we have no idea about if there is some exoplanet or some planet somewhere else. Imagine that. So in 95, I had 2 years at the time. So we discovered the first exoplanet. Now we are looking at the atmosphere. That's just a big shift I would consider in technology that we are doing today to advance our understanding of astronomy and astrophysics. And I will also talk about, since I talk about the SITE, which is the search for extraterrestrial intelligence. So China is building one of the largest telescopes in the world, like almost half of a kilometer. So between mountains, and it's fixed, and they're trying to look for aliens. Imagine that, a lot of money, a lot of billions here too. So, and trying to, if the telescope is always now, I think it's already operational, and they're trying to see if they can receive some signals from somewhere. And you have seen that in movies, I believe so, but now people are trying to do that seriously, and we see if there is any aliens somewhere else, and look at the technology to build a telescope with like half kilometer, like 500 meter in diameter, which technology we're using here, just amazing and crazy, and how we're advancing these things. And I will finish with showing some pictures that change a bit how it changed our way to look into the universe. So this is one of the first pictures that James Webb took, and you see how it's sharp and shiny pictures showing all the stars here, and also the dust and the interstellar cloud, what you call it, in the universe. So I did not show the picture that we took before that from the ground base and with Hubble and with James Webb, but this is one of the sharpest pictures that's showing how the technology is shaping and changing our way of seeing of understanding more and progressing in the astronomy. And of course, this is the ALT, so now it's been in construction, so it's almost going to be having, in a couple of years, we'll be finishing, and we'll be also looking at the exoplanet, and I will show this video, show how big and how it was, the telescope. I had the chance to see it when it was nothing on this mountain, when they the ESO, European Southern Observatory, they just cut the mountains to put this giant telescope here with a 30-meter of the diameter of the mirrors, and almost more than 700 segments of mirrors that they are moving at the same time, trying to calibrate and trying to remove the artificial fluctuation of the atmosphere to have a sharp images and also to take the best images of the universe that we are looking through. So that's to show, and we still have a lot of, there is other similar telescopes that are being built like TMT, 30-meter telescopes by the Americans, and we have GMT, and we have many other telescopes on their way. So humans are progressing to understand and to trying to confirm or to prove what we have thinking about the universe and how the universe is evolved. And if all this question that I have shown today in this conference about the life beyond Earth and also how the cosmos, the CMB, and we are trying to look at the first waves that produced by the Big Bang, so from CMB and so on. And I will summarize by saying that the technology that we are advancing today, it's really shaping and shifting our understanding of the technology, and this is also will not stay. The technology that we are developing is not gonna be only focusing on what we are doing in astronomy, but also could be applied to some other lives, application in our daily life that we are having, like from satellites and from many other application and so on. So that's to end here, and thank you very much. If you have questions, please. Yes. Oh yeah.
Like that? Non, c'est bon, je le prends, parce qu'après c'est les autres qui... Yeah, like that?
Yes.
Yeah, just, I have two remarks and one question.
Yeah.
One remark is about the very word astrobiology. When I started to be interested in this field, it was called exobiology, as far as I remember.
Yes.
So I'm wondering why they started to, because in fact, to say astrobiology, it just seems weird, because the idea, the basic idea is that we think we know that life with the word biology is only on the Earth, so that's understandable that you say exobiology. Is there a life somewhere else? And so it becomes a specific discipline. While when you say astrobiology, yes, right, but it's also here. My second remark is the very word that I've never understood, exoplanet. What does that even mean? I mean, it's just a planet. And it's the other way around this time. Why do you use the word exoplanet? We are looking for other planets than ours. We know it's a planet here. And we know there are planets. So we don't need to say exoplanet. It doesn't mean anything to say that. So I think there is something to change here.
Yeah, these things are related to the exo ones. I will explain to you why.
Great.
So we mean by exo is something outside of our solar system. We think that we are unique. Well, we are not.
And that's the point, we are not.
Yeah, I agree. Just kind of.
After Copernic and all that, I don't understand why we still say.
Yeah, it's just like it's just a kind of reference that we are using. So when we're talking about exo, means talking about something outside of our solar system, not on our planet. And this is why we mean by astrobiology. We do not say exobiology, because astrobiology, it means that we can also look for life just in our neighbors, like Mars. And Mars is not exo, it's just in one solar system. And that's why we don't use...
astrobiology, not for exoplanet.
Exactly, yeah. Exoplanet is something, just a reference, like, because we know what's happening around our star, but when we talk about something outside of our star, then we use the word of exo.
Exactly. And but when there is a shift in perception, it's also that there is a, I mean, the words themselves, they actually express the shift of perception. My third...
Yeah, I will ask you another question.
It's a question.
What we're going to name something is for another planet, find another galaxy. Because this thing that we're talking about, it's only in our galaxy. Yeah. Imagine if one day, and I think this, if we improve our technology, and we find the planet in another galaxy, not in our galaxy Milky Way, maybe in Andromeda. So what we're going to call it? Exogalactic planet, so it just names.
We can say the field of exobiology, and after we specify it inside.
Yeah, it just
anyway, well, it doesn't matter.
The same new actually. It might be changed. Huh?
Okay. And but I have a specific question about because at first when we were looking for alien life, and it's true, you have mentioned the question. I've always been very skeptical about the fact that we are actually looking for what looks like us. I mean, at least what looks like what is, I mean, basically, as you said, carbon-based life. And so we're thinking a priori, not anymore, but we were thinking for many years that what we are looking for is actually the very definition of life, what in fact it's just the very definition of life on Earth. And so there is kind of a bias here. So my question is, because there is some research that are trying to challenge the idea that life is forcefully based on carbon, saying that silicon-based life. Why do you think about this theory? Do you think has it advanced a little bit? Do we have other hypotheses? Because I heard about this thing about silicon-based life. Is that possible? Do you work with people that try to feed these hypotheses? Do you have other hypotheses, or this is maybe totally fiction, or I don't know?
Well, yeah, you're right. So it has been a fiction for a while, but I think no, it's not fiction anymore, because we're looking and trying to look at this molecules in this exoplanet. So, and we will see. So, but we will be never able to like try to look at things in real. So it just, yeah. So who knows? So for me, I believe in that. So they might be. Yeah, I do so, because we are talking about, because all this thing that we are talking about is only on our galaxy. So if we want to do some statistics in our galaxy, so we have almost 1 to 2 trillions of planets like our planets in terms of density, in terms of like terrestrial planet we call them, like Mars and like Earth, 1 to 2 trillion. That's how I will think that maybe there is something. We know that's maybe something maybe different from the life that we used to know here, based on something else that we are not aware of. So we know only about life that we know, but maybe there is another kind of form of life. It might be created by the. Sorry?
We live in a huge diversity. That
Yeah.
there's not some kind of a uniformity of the components in the different planets.
Yeah. Why not? So I think so. Yeah. Yes.
When you are talking about life, you are talking about the same condition as
No.
our condition, or we can have life with other condition.
No, I mean, first, because we have a really high number of the planet that we can see, a range of number of planets. So first we have to just narrow where we are looking for some, like, let's say, basic conditions, like of having liquid water, as we know.
Yes, but this is our condition. Maybe we have another liquid, another.
Maybe not. That's what I mentioned. Maybe it's not based on the. But now we were trying to find something similar to us first, because this is something.
We need to start with something.
Yeah, exactly. We need to start from somewhere. So, and we start from something that we know. But does not mean that we are excluding all the other possibilities that for other planets they maybe have. They can based on different chemical element, not water, maybe. But and what we are doing, this criterion, this condition, to first look about the emission of the water in this exoplanet and try to link it to what is on the ground of the planet. And okay, we can see that something maybe similar to our Earth exists somewhere. It's a good advancement that if we can achieve, and we are achieving it now with James Webb. And this is one of the reasons why we built James Webb like for the last 10 years, and it costs all this money, and we are building more new telescopes like ELT just to look for that. But after, so the floor is open, so you can go search for something that you can imagine as something and try to look for it, but good luck with that. So we know how to.
Also asking, yes, the question with the condition is a very interesting question, but what I was also asking is, are there people here that will be like exobiologists or something that will try to do some research on the possibility on Earth, not astrophysicists looking outside, but saying, okay, if we think it's possible, let's try to make some experiments what could be this silicon-based life. Are there people, laboratories, research centers trying to work on that specific field, which is a little bit different than from astrophysics?
Yeah. There are some people that are trying to do that, and one of them is KV Lob, who was invited last year to and he's looking for this, Ivy Lob, yeah. He's looking for this meteorite, and he believed that it's coming from somewhere where life exists, and trying to analyze them on here, on the labs here on the planet, try to find what they are made of and so on. So yeah, there are some people, but always you have something to start with, and you can go. Yeah.
Oui, maybe I will ask in French. Is it
Yeah,
okay,
fine,
the
it's
question?
fine. Yeah.
Bon.
Super.
Oui, alors d'abord pour l'histoire. Merci beaucoup pour cette présentation très intéressante. Pour l'histoire, alors c'est un peu nos efforts, c'est on oublie quand même des grands noms du monde arabo-islamique et en particulier Copernic n'est pas vraiment ne marque pas le début d'une révolution, mais c'est le dernier maillon de l'astronomie, en particulier de l'école de Malaga.
Ouais.
Et en fait, c'était un peu une hypothèse pour laquelle il n'avait aucune preuve, alors que l'hypothèse héliocentrique était déjà discutée auparavant, mais il n'y avait pas vraiment des observations qui permettent de la valider. Et donc,
c'est Galileo qui l'a validé.
Oui, c'est après, oui, effectivement. Ensuite, je me pose la question, nous, maintenant, en tout cas, dans mon laboratoire et autour de moi, on commence à se poser la question, est-ce qu'on a le droit de se poser n'importe quelle question dans la recherche, vu la situation, la crise, le désastre écologique? Est-ce qu'on peut se permettre d'aller explorer la vie avec des moyens technologiques quand on a une vie menacée sur Terre? Donc, je ne sais pas ce que tu en penses. Voilà.
Yeah. Thanks for the question. So, d'accord, oui. First, thanks for the comment. So, I'm not really a specialist on the history of science. Maybe I will miss something. And yes, I know. I was busy this morning, but I should attend it, of course. But I know that there is some. I did not highlight everything and about all this accumulation work that has been done for each shift. I just try to choose one of the main figures to see how things shifted from one place to another. So coming back to your question, yeah, I totally agree. So we should first, this is why I say there is no plan B. So even we find other planets, we cannot go to them. So actually, but it's just a question of wondering. And it started with humans since it's derived in human, just wondering. So finding their place, so they are trying what's there, finding continents, finding new places, and then finding planets surrounding them, and it's still going. This is, I think, something we never can stop because people will always.
I agree with you.
Yeah.
It's not for practical reasons, but
Yeah.
Even question
Yeah.
our priorities.
Yeah, maybe. Yeah, that's.
There are other questions also we could ask about. We could be curious about the life here, right?
Yeah. We should. This is.
Have a lot to know about even the creatures.
This is definitely. I agree with. We really should take care and trying to take care of our life here. So try to make it better and trying. There's a lot of problems happening here in our planet, and they will add more because I know people they are wondering about the climate change. But I always in my presentation I add, okay, there is some menace, some dangers coming from outside, which is the asteroids. Actually, nobody talk about them. So they can destruct life in Earth too. So we should now with NASA and ESA, they are trying to develop some techniques and some method how we can deviate these asteroids if they are coming to us. With many methods, and actually I'm really involved in that, and I like to work on that because this is one of the dangers that can also distract life on Earth, alongside with the climate change and what our humans are doing. So I agree. So the priority, and if you look at the budget of things, the budget that we are allowing to these things, and now even with with Trump and with new administration coming to the U.S., they are reducing things. So if you compare the budget that we are making on space exploration, it's really nothing compared to what people are expending on the wars and on many other things. So if you look but for me, my opinion, so we should never stop people thinking about the horizons and trying to go farther as much as they can to understand. Because if you ask this question when we have. If we did that since the beginning, so we will not maybe understanding how much we are understanding today about how the universe works and how what is surrounding us. But I agree. So and this is why in Morocco we still did not have that much activity in astronomy and development in astronomy. Because it is not their priority for now. But does not mean we should not. Stopping people like thinking about that and trying to get involved in these things. Maybe this is also I believe so that's having people dreaming about going to Mars or to go in is something it can create some innovation and also build their thinking capacity. So people that think out of the box, not only thinking about Earth, but our Earth should be the priority. Yeah, actually, yeah, I totally agree. Yes?
Bonjour, merci pour cette présentation. C'était très riche, très intéressante. Pour moi, je veux juste savoir votre point de vue sur le projet de Elon Musk, qui est le fondateur de SpaceX. Il veut coloniser la planète de Mars, il veut envoyer des humains d'ici 2029. Donc ça sera possible ou quel est votre point de vue?
Yeah, merci. Et maintenant, il est porté par Trump. Hein, so yeah, actually, I like what Elon Musk is doing. So having some, actually, he changed a lot of things on the space. So with the own way of innovative way, how it changed how we can use rocket. We never thought that we can have reusable rockets. Now he's doing that. So for me, I don't care about Elon Musk himself, but I care what he's bringing, his energy that he's bringing, and the investment he's bringing to the space. So I agree. I like what he's doing, and I'm totally supporting that. So since it's a private, it's not public, so he's making that from his own money, so nobody's going to ask him what they're going to do with his money, and everybody's free to do whatever he wants to do with his money. So, and I think, I believe, I hope that we have many Elon Musks around the world, so to do that. And well, so people have different opinions about that, but my point of view is just, even we go, I don't like this word of colonization anymore, because what does it mean by, now we have been in the moon, we did not colonize the moon, so everybody have access to the moon. But just, this is, for me, the competition and the challenge is always good. So, and this is what bring the US and the Russians so to the moon. If they did not compete, they would never be in the moon. So they were competing, and this is can take out the best of you to advance your technology and so on. And I like to do that also for Mars and for other planets. So now we have many. You see, you have thousands of planets. So colonize whatever you want. So there are many. If you can go, just go. But just like this is some, and this is show that we are different. So some people like they won't just take it out. Some people will just no, we don't need to go there, and that's why we are also the difference in our opinions and our ideas.
Yeah. Thank you so much, Youssef, for this beautiful presentation. It's always great to listen to you. And thank you for your openness not to mix a lot of political point of views with science, like raw science. And I have maybe 3 questions, if I still recall them. The first one is about, were there any Arab astrophysicists back then, before Newton, after that? Because there were like some effervescence, intellectual effervescence back then at IAS-UM6P. We love reminding that there is like some Arabic touch out there. And the second question was about James Webb Space Telescope. Was it like an international collaboration? Because if so, maybe it embodies this idea that we're all in it together, and all these conflicts we were talking about is something really absurd. And the third question is about quantum physics and how this parallel universes and realities should apply to this universe that is infinite, but at the same time expanding.
Yeah, thanks, Marwan, for your questions. But the first and last question, so I will direct you to but I will give you my opinion. But maybe I don't have. Maybe I know that there is a lot of Arab and Muslims who's developed working in astronomy. At that time, they work in astronomy, math, physics, and chemistry, and everything. And this is people who study really the history of science, so they can tell you more about details. So actually, but I know that there is some really contribution from the Arab and Muslims in general, so to the understanding on astronomy, and because they will use it to travel, and there is a lot of, and even the names now in the stars, most of them are in Arabic. So that means that they are named after scientists. Yeah. Yes.
She's
Yeah.
professor.
Yeah.
She's very famous.
No, we were talking now about the oldest one. So, and but now there's also some
We have Youssef Moulane.
scientists. No, not. Yeah, there are some people who could not study astronomy here. They go abroad and they study it. Now there are some people at NASA, there are at ESA, there are some people even at JAXA. So I know some Moroccan people working with Japanese, and there are some people who now the world is, and there's also from other countries, not only from Morocco, from other Arab and Muslim countries. So they're working in Europe, in the US, and also in China, and so on. So there is some contribution. So from your second question, so about James Webb, it's international collaboration. The short answer is yes, there is international collaboration, but it's the two mainly players, so the Americans, because they are funding, and also the Europeans. So, and there's other countries, of course, it depends how much they are investing in that. Unfortunately, there is no Africans because Africa astronomy is not our priority for now. We are still struggling with many things, but in the future maybe we can try to allocate some money, some time for that to advance this field of astronomy and astrophysics in Africa. And I'm actually personally involved in that through the African Astronomical Society. So I recently was elected as a committee executive in the association, and we're trying to expanding and developing astronomy and astrophysics in Africa. And next year we're going to Botswana to host the General Assembly, the conference of the African Astronomical Society. So yeah, but means that if this is an international collaboration, but it's not closed, so the data is open to everybody. So anybody can work with, anybody can apply for time on James Webb. I have already applied twice, but unfortunately I could not get the time because it's very competitive. But with other teams in the USA, we got time to observe comet. That's my field when we do comets. So, and it's costly. So like, I think 1 hour, it costs like a few $1,000s. So it's not easy because one of the most powerful technology that everybody wants to use around the world, so from everywhere. So, but the good idea about that, it's open, everybody can apply for it, but and see which your area that you're bringing to observe with this 10 billion instruments is so crazy. And it's good. And your last question is about?
Parallel universes.
Oh, the quantum and parallel. Yeah, there is, maybe John can also jump on that. So about multi-universe theories. So there are many ideas. Now we believe in, I want to believe, but we have one of the famous theories is the Big Bang. We're trying to prove it. But there are some people proposing many other crazy ideas. So maybe John can...
I don't know. I'm really not a specialist. But, clearly, the multiverse has become some kind of a scientific question, although we know that we probably cannot, probe it. But it is there in the field of cosmology and quantum physics as well. Yeah, exactly, because there are several levels of multiverse that we can talk about. I mean, there's the quantum physics multiverse, which one of the interpretation of quantum physics says that every time there is a projection, the universe splits into many, so it's a possibility. But also, just if you look from the point of view of simple cosmology as we understand it today, if the universe is that large, if it's infinite, well, one could question the pertinence of the word infinite when we talk about the real world, but if the universe is infinite, then there is some kind of a multiverse in the sense that there are replications of us, an infinite number of replications of us. So that's some kind of a multiverse. So I think it has really become a relevant question, but the hope to probe it scientifically, experimentally, empirically, is extremely small. So I guess it is likely to remain an interesting question, but not so scientific.
Some more questions?
If people are interested in giving the time machine, you can log on SETI at Home program and download it. And when you're not using, when your computer is idle, it calculates the programs coming from the large telescopes.
Which one again, sorry?
SETI at Home.
Oh, SETI at Home, yeah. So this is one of, we call it this citizen science project you're talking about. That's, yeah, again, so back to the question about this, that it's data, it's open to everybody. So not we are only scientists that we can benefit from this data, but there is some data, it's open to everybody. So even students, they are not studying astronomy. So I see some students here, they came from the IAS-UM6P, but they are interested in space and astronomy. And this is why we have many, what we call the citizen science project, that people can help us to find more exoplanets, for example, or to detect new planets or the signal of the planet, or maybe have some ideas about creating some tools, how they can help us to analyze the data and so on. And you just create NASA citizen science, you will find more. And I think Europeans also doing some kind of project. And this is one of the questions that we are addressing. We want to be inclusive. We're not doing something somewhere else alone. We want to include everybody with us. So trying to make it easy and trying to create to include the society. So like from different levels. So to help us, because it's not only our mission, it's the mission of everybody to understand what's happening. Everybody, I think, is wondering what's happening surrounding us and want to understand and so on.
Merci. Thank you.
Thank you.